Good morning, good afternoon, good evening, and welcome to this introduction about Inventor ETO. My name is John Balkley, and I'm on the Inventor ETO product development team. Today we're going to look at this particular model of pressure vessels, and we're going to look at how you can use your Inventor models to create an ETO model. Inventor ETO is, of course, built upon Inventor itself. And that shows that the most important part, the core part of your ETO project will be your Inventor models themselves. On top of that is the Inventor API layer and, of course, the parameters of the model itself. These are what ETO can drive. Wrapped around that is the ETO system itself. And this is the mechanism that will drive your Inventor models. Further around that are your particular ETO rules and parameters themselves. And we'll see how you can write ETO rules that wrap around your Inventor models. And then finally, at the outer layer is ETO's API and custom user interface. These are what the end user will see when he or she wants to interact with an ETO model. But today, we're only going to be looking at the inner layers, just the ability to define the ETO model on top of the Inventor model. So we will not be seeing a very beautiful end user interface, but rather we'll be looking at how you can create the models themselves. So since the Inventor models are the core of your ETO model, let's take a look at some of the components of this tank. These are the tank components themselves, the shell, the main shell, and the two kinds of caps. And you can see that the caps all have the same parameters, that are same relevant parameters, diameter and thickness. ETO rules are created using Microsoft's Visual Studio platform. This is a new feature of our R2 release. The first thing that you'll do is create a new project, and there's a template for a design library project, an ETO design library project. You can give it a name and then browse to a particular location, and then you have an option of choosing to add this project to the source control mechanism. This is often key where ETO projects are large. Anyway, we continue on, make our new project, and you can see that ETO automatically creates a sort of template project for you with some built-in mechanisms right off the bat. Our next step is to go to the Inventor components and adopt them. This is a tool inside of Inventor ETO that automatically creates an ETO wrapper around each Inventor part. It gives us the ability to control the parameters of the part from ETO rules. Now, back in ETO Studio, let's take a look and see what has happened. Under the Adopted Components category, you can see the 4 adopted parts. We can look at the design for each one, and there's 2 levels here. At the lower level is the actual work of wrapping the Inventor part with the intent rules that wrap the Inventor parameters. Our next step is to create a design that represents the assembly of these components. So what we'll do is create a new design. We'll give it a name, call this one Tank Assembly, and we'll say that this is a kind of assembly document. And that creates a new blank assembly design for us. And you can see here's the blank design there. Then we'll add a child rule for each of these components, for 2 components anyway. First, we'll enter a child rule for the shell, and we'll indent this over a little bit. And then we'll add another child rule for one of the caps. Then we save this design, come over to the ETO model browser, and say, let's look at this one rather than our default assembly. So we changed it over to the tank assembly. Switch back over to Inventor. And you can see that in the Inventor assembly now we've got these two components here. We can just take a look at these, rotate around a little bit. You can see that the cap is loose, right? There's no positioning constraints yet, and so they're just kind of floating in space. Back once again in ETO Studio, we're going to enter some parameter rules. These will allow us to control the assembly in sort of high-level ways. In order to do that, we're going to also pass these parameter values down into the children. So here we're saying that the diameter of the shell is going to be equal to the diameter of the assembly, and the thickness of the shell will be equal to the thickness of the assembly. Ditto for the elliptic cap, the diameter of the cap is going to be the diameter of the assembly, thickness will be the thickness of the assembly. Now we have the parameters the way we want them. We'll click on Save. We'll switch over to Inventor and take a look at the model. You can see now that the diameter has changed. Come back to ETO Studio. We'll change the parameter values. Here we can just change them to any arbitrary value, and we'll make the diameter be a little bit smaller. Switch back over to Inventor, and you can see that now it's a little skinnier. Now we'll come back and change that again. Go back to parameters, change it from 500 to 200. Click OK, switch back over to Inventor, and you can see now it's really skinny. Now you can see that the names in the child rules are the same as the names in the component hierarchy. I'm going to change these names because I want to. Change this from shell 1 to shell, and from cap 1 to just cap 1. Hit save, and you can see that the model will change to show the new names. The length of the tank assembly is supposed to be the overall length, so we need to make the shell be a little bit shorter. So we're going to define a rule for the shell length. We're going to say it's numeric, of course, and it's going to be the overall length minus the cap's height. Cap has a height parameter, and of course there are going to eventually be two caps, so we'll multiply that by 2. And then we'll use that to pass that into the shell. And we'll say that its length, and here's the case where the names are different, the length of the shell, is going to be the shell length. We hit save, come over to test that, and you can see that now it's quite a bit longer. Come back to ETO Studio, change the parameters, we'll make the diameter be a more reasonable diameter. Click OK, switch back to Inventor, go save, click back to Inventor, and you can see that now it's got a more reasonable value. And of course the cap is still independent because it's not constrained. So here you can see that the cap is not constrained. So we'll quickly add a few constraints to lock it in place, going very fast here. Once the constraints are made, then what we can do is bring them into ETO. By right-clicking on the constraint, we can select Adopted to Intent Model. Put this in, and we'll do this on each of the 3 constraints. So we'll click right on it, adopt it into the intent model. And finally on the 3rd one as well. And then switch back into ETO Studio. Allow it to update. And now you can see that ETO has written 3 new child rules that allow us to drive the constraints from ETO. Now you can see that the elements in the model browser have the same names as the child rules in the design. So I'm going to change the names of the constraint children so that they have more reasonable names. We'll hit save, and you can see that the names change. And now what we're going to do is duplicate all of these so that we can have 2 caps and have the second cap also be constrained. So I just copy and paste the text of the rules, change the 1s to 2s, and then hit save, and you can see that I have my second cap and second constraints. I happen to know that there's a constraint failure in this case, so I'm going to change a few things and then switch over to Inventor, and you can see that now we have our full tank assembly. Now we're going to go through the same process for the components of the legs, or as it's called, the saddle. Here we're going through the adoption process of the individual components. Next, we're going to create an assembly for the leg design based on an assembly document. Here's our blank assembly. Now we're going to add child rules for each of these components. We'll give them nice names to begin with. We're only going to do 2 parts for this leg. We're not going to do the full complete part as we saw in the original in the beginning. Here you can see that the 2 parts are not constrained yet. We're going to add some parameters for the assembly. You can see that nothing really happens with that. Now we're going to quickly add a whole bunch of constraints. La-di-da, same as before. And now you can see that the components are constrained together. And then finally we're going to pass in the parameters of the parent down to the 2 child parts. Save that, and now you can see that they have the correct size. Now we're going to switch over and start working on the top level assembly. This is called the pressure vessel assembly, the first level design, highest level design. You can see that we're changing over to that, switching over to the rules for it. You can see it's empty. This is how it was originally created. We're going to use the same insert child rule command, but now we're inserting a subassembly. We'll indent that over a little bit, rename it so it's more looks like a better name, and then we'll do the same thing for the saddle leg, so that we've got one leg in the assembly. Again, we're going to insert, tab that over, and then change, and then give it a little space, and then we'll hit save, save, and then switch over to the Inventor model, and you can see that, oh, we've got the 2 components there, but they're not quite the right, they're not sized relative to each other properly. So we'll switch back over to ETO Studio, and we'll go to the top of the design and enter a new parameter rule. This time we're going to control the diameters of the tank and of the corresponding cutout for the leg through a top-level diameter parameter. And we'll pass that into the tank child. And I think we need to spell that correctly. It's always best to spell things correctly. And then we're also going to pass it into the saddle leg, but it doesn't seem to have a diameter parameter. What do we call it? We'll look through here. I don't see it. So we can stop this, and we can switch over, go to the saddle leg design, click right on it, and say Open Design, and then we can look at it and say, oh yeah, there it is, shell diameter. Okay, so now we can type it in again. Now it's right. Now we find it right away, and then we can hit Save. Go back to Inventor, and pan around, move it around a little bit. And now if we look at the top view, we can see that the cutout matches exactly. The next step is to add constraints. Since we've already seen how to do this, I've sped the video up by a substantial amount. Here you can see that we're doing the first constraint to get the vertical alignment of the tank to the saddle. And you can see that that's partially constrained. Then we're going to get the lateral alignment. We're adopting it into the intent, we're renaming it, and now you can see that it's partially better aligned. And finally, we're going to do the longitudinal constraint, change the name of that, and now you can see that it's constrained. The next step is to add the second leg, and to do that, we're going to switch over to ETO Studio. What we're going to do is to add the number 1 to each of the constraint children. and we'll hit save and check to see that that's actually working. Yeah, okay. And then what we're going to do is select this entire region, copy and paste it, copy and paste it, select the region again, and now we're going to use search and replace to replace all occurrences of _1. Again, we're just using the standard Visual Studio tool here with _2, replace all. Let's do this little thing here. Okay, close, and then we'll hit save. Hit save. Oh, we'll change the value a little bit, and then look at the result. Of course, these are not really the correct longitudinal positions for those legs. So what we're going to do is add some more rules to control the longitudinal position. What we'll do is add a parameter called the length, and that's going to control the length of the entire assembly. And then we're also going to add a rule called leg inset, which will control the obviously how far in the legs are. And we'll set that to 0 just for now to see that it does the right thing. So we're going to set the length of the tank assembly, and then what we're also going to do is change the offset of the longitudinal constraints. So we're going to say that the first one is offset by the leg inset, and then the second one is going to be offset by the tank assembly's shell length minus the leg inset. So that pushes us all the way to the end of the shell and then backs us off by the leg inset. We'll hit save, go over to Inventor, and we should see that the legs are at the appropriate end positions. Let's see what happens if we change the value of 0 to a bigger number. So we'll do this in a slightly different way. Change that to be 250, hit save, come over to Inventor, and there we are. The next thing we're going to do is very interesting. We want the assembly to support 3 different kinds of heads or caps. So what we're going to do is switch over to the tank assembly. We're going to add a new parameter here called head type. And this is going to allow us to control which type of cap to use for each at each end of the tank. And so by default, we're going to set it to be the same, the elliptic cap. And what we're going to do here is copy this text and change the name of the design to use for the child from being a constant to a variable. So now we can choose what kind of head type to use. We're going to switch over to the top level design and also add the same kind of parameter here so that we can pass it from the top level down to the subassembly. So we put this second rule in, pass it down to the tank subassembly, and then we'll hit save. Sorry, and then change the parameters. This is an artifact of the video, and we'll go to try the flat cap type. Switch over to Inventor to see what it looks like. Voila, you can see that it's using a flat cap. Now we'll change it back to hemispherical cap. Hemispheric cap. Switch back over to Inventor, and there you go. There's our hemispheric cap. Really, the 3 kinds of caps are defined by the ones that we adopted, but any design that matches the right parameter types will work. Now, these designs don't exactly map to individual assembly files. They're more like a recipe to generate assembly files and part files as necessary. So what we're going to do is to make a test here that creates 3 different pressure vessels of different shapes and sizes. So we're going to create a new top-level design called test tanks. We're going to add, just like we did before, we're going to add the pressure vessel this time as a child rule. And so now we've got a super assembly, which is going to use our main assembly as a sub-assembly. And we're going to specify the head type for this one to be elliptic. And then we're going to copy and paste this 2 more times and change the head type for the other ones. So here's our second one, change that to be flat. Here's our third one, change that to be hemispheric. And then we'll save that one. We'll switch over to using the test tanks design. Switch over to Inventor. And then you can see, oh, we've got the 3 tanks here. Let's move them around a little bit so we can catch a better look at them. And you can see that they have the three different head types are all shown. We can also change the sizes of each of the tanks. So we'll make tank number 3, that's the hemispherical one, we'll make its length be a little bit shorter than the default at 2000. Save that and go back over to Inventor. You can see that's a little bit shorter. Now the flat cap one, switch back to the rules. Flat cap one, we're going to make that be fatter. We'll change its diameter from the default value to be 1800, a little bit bigger. Save that, come back over to Inventor, and you can see that that updates, and it's a nice big fat one. In this next section, we're going to show how you can use non-geometric rules to control geometric properties of the model. This is essentially engineering to order, ETO. First, we're going to just take a little bit to review which one is which. That's number 1, that's number 2, that's number 3. We'll switch over to ETO Studio and go to the pressure vessel assembly design, go to the top of the file, and then we're going to enter some more rules here. So first, material density, then max volume. This is going to be the volume of the entire cylinder, including the caps at the end. And then finally, the weight based on the density times the volume. Oh yeah, we need to fix the units there. Now we're going to use the model windows in ETO Studio. So first we're going to select the first pressure vessel and then go into its properties, double click on the values, and look at the resulting numbers. So now we're looking at the second one, the large one. Double click on that, yeah, density is 1. Volume is quite large, and so the weight is quite large. And then go to the third one, and we can try that again. What we'd like to do next is change the thickness of the legs in proportion to the weight of the tank and its contents. So the first step that we'll do is put in kind of a dummy rule to just test out the capability of doing that. We'll call this web thickness, and then we're going to pass this value in to the 2 leg parts. So we'll say the thickness of saddle leg 1 is the web thickness, scroll down, and the thickness of saddle leg 2 is the web thickness. We'll switch over to Inventor, and check it out. Zoom in on that, use the measure tool, distance tool, and see that the distance is 25 millimeters. So let's change that rule so that the web thickness is now going to be dependent upon the weight and a safety factor. So what we'll do first is just comment out our dummy rule and then start a new rule with the same name that is a lot more complicated. And this is very typical of most real ETO applications. So we're going to make the safety factor be 2.0 and say what's our lightweight material thickness, what's our heavyweight material thickness, what's the factored weight, weight times safety factor, and then what's the maximum for the lightweight material, If the factored weight is greater than the max, then we're going to use the heavy weight, otherwise we're going to use the lightweight, and then we're done. Switch over to Inventor to check it out. It looks a little thin. Let's measure it and be sure. Click that one, only 10 millimeters. That doesn't seem right. Let's zoom out and look at some of the other ones. Well, there should be 3 of these in here. So well, that one looks thin too. I wonder what let's measure to be sure. Yeah, that one's all, I wonder what's going on here. Well, there must be some kind of mistake there. Let's go back to the rule and see if we can figure out what's going on. So we switch back over here. I'm going to put in a couple of extra little things in here that will help me debug this problem a little bit. First, I'm going to put in a little extra rule that will help me identify which part I'm working on. I'm going to use this ref chain rule. And then I'm also going to assign a variable called WT, so I can pull out the weight of the current part and change the use of that down there. And then what I'm going to do is save that, and I'm going to set a breakpoint at the beginning of the rule. Save that, and I'm going to hit the breakpoint. And now what I can do is use my debugging tools, the regular debugging tools of Visual Studio, to look at the call stack and look at the local variables. So here you can see that I'm in the web thickness rule, and I can scroll up and look at the local variables of that rule. And I can step over line by line and see what the results are. So here I'm looking at, I'm on pressure vessel number 1. Step over that, I can see what the weight is. Step over that, I can see what the safety factor is. Step over that, I can see what the lightweight material is, and so on. Now, when I'm ready, I can go on using the continue command, and that will and that will take me to the next breakpoint here in the same rule, but on a different part. You can see I'm on pressure vessel assembly number 2, and I can look at the values here. Looking at the values, stepping over, thinking about it. The factor weight looks kind of small. All right. Let's continue. Okay. So we're at the breakpoint again. We're at part number 3, stepping through. Yeah, weight seems right there. Yeah, factor. Factored weight seems real small. How come the factored weight is so small? Oh, there's the mistake. All right, well, let's continue. Switch back to ETO Studio. You can go to the rule in question, fix the error, change it from 2 to 2.0 as it was meant to be. Press save. It brings us to the breakpoint, of course, again. Now we can either step through it or we can continue. So now you can see that that's the weight. Step through it, step through it, step through it. Factored weight, oh yeah, factored weight looks right now. Continue through the rest of it. Continue. Put the model. Oh yeah, now it looks like that we have the thicker material. Yes, 20 millimeters. But now we'd like to see what happens if we use a lightweight material. So we're going to go back to ETO Studio. Now we're going to use this new parameter called material density. We're going to try making a tank full of air. Density of air is 0.0012. Hit save. Come back over to Inventor, and now we can see that some are thick and some are thin. Well, thanks for watching this little video. I hope it was informative and piqued your interest. If you have any more questions, feel free to contact someone on the ETO team.